right? So coming back, I already emphasized this, the amount with which this will be decreased will be same amount it will be increased. That means how much it will take? An electron goes to this, will be having, can we have 0.4 students? I'll repeat again. So this is splitting, that is between the T2g and EG orbital. This is T2g orbital for you and this is EG orbital. Just rub these things. Let me make it clear this portion. So the splitting, this is dxy, dyz and dzx, right? This is T2g orbital. So splitting the, the energy gap between the T2g and the EG orbital is basically delta naught. Okay, so 1 delta naught is equal to 10 dq, right? They may ask you this is our CFSC calculation, it's required, crystal field stabilization energy. They may ask you how many delta naught will be having or how many dq will be having. So that is, what I mean to say is, see, an electron if it is going to dxy orbital, it will be stabilized. Stabilized means negative charge we have to give because it is decreasing energy. Energy wise it is decreasing, so you will be putting hypothetical energy level, if you are putting 0, this will be negative. How many it is taking? For example, this can I put it as 0.4, 0.4 and 0.4 for 3 dxy, dyz, dzx. Altogether we will be having 1.2. So this we can make it as 0.6 and 0.6 because, so total amount should be same. That means any electron if it is going to the T2g orbital will be stabilized by minus 0.4 delta naught, minus 0.4 delta naught or minus 0.4 delta naught or 10 dq, sorry 4 dq, right? Because 1 delta naught is 10 dq. Any electron if it is going to the T2g orbital will be stabilized by minus 0.4 delta naught or minus 4 dq. Clear? On the other hand, any electron if it is going to the EG orbital will be destabilized by plus 0.6 delta naught, plus 0.6 delta naught or 6 dq, plus 6 dq. So this is how it has to be done. Very clear? So I'll just put it back. Minus 0.4 delta naught or minus 4 dq or plus 0.6 delta naught or plus 6 dq will be the stabilization. For example, if one electron goes here and one electron goes here, altogether I will be having 0.4 minus 0.4 plus 0.6. That means it is destabilized by plus 0.2 delta naught or 2 dq. Clear? So that is how we will be calculating the CFSC, that is the crystal field stabilization energy may be asked to calculate, students. That is the crystal field stabilization energy they may be asking you to calculate. So we will take one by one, few of the complexes we will take it. I am talking about the octahedral complex. We will take some of the octahedral complex and try to predict the crystal field stabilization energy, which may be the one thing which will be asked, that is crystal field stabilization energy. Crystal field stabilization energy, which could be asked, that is what is called as CFSC. They may be asking the CFSC for octahedral complex. Let us take care. So we'll go for one by one complex very quickly. Titanium 6 times 2 plus. This is the complex I will take, complex ion I am taking. Titanium, that is 22, oxidation state is 22, oxidation number is 22, that means 3D, it is D2 system, 3D24S2, very clear, 3D24S2, 2 electrons from the S orbital we had removed, that means we have 2D electrons left out, right, 2D electrons left out, and it is an octahedral complex because there are 4 coordinating atoms, there are 6 monodentate ligands are there, hence it is a octahedral complex. So how many electrons we have? D electrons, 2D electrons. How do you write the electronic configuration now? The electrons, whenever you are filling the electrons, you have to follow Hofbauer principle, Hund's rule, the Pauli's exclusion principle, all those things has to be filled. That means lower energy will be filled first, then we'll be going for the upper energy. 2 electrons are there. How do you fill? These 3 are degenerate orbital. That means this is a triply degenerate orbital. Triply degenerate. That means 3 orbitals are of same energy. Triply degenerate. And this is a doubly degenerate. This is a doubly degenerate. It's a doubly degenerate orbital, right? So triply degenerate orbital and a doubly degenerate orbital you are having, right? So now you 2 electrons you are having. How do you fill? You have to fill singly fill it. Whenever you are having degenerate orbital, you need to go for the singly filling. Afterwards only you are supposed to pair. So what will be done is, I will put 1 electron in this, another electron in this. This will be empty. Very clear. So 2 unpaired electrons you have. Each electron going to the T2G orbital will be stabilized by 0.4 delta naught, because amount with which destabilizes, that same amount it has to destabilize. That means 0.4, 0.4, 0.4, 1.2, 0.6 plus 0.6, 1.2. It has to be same. Plus minus, it will cancel. So hypothetically it will come 0. Right, that is how it has to be. 2 electrons you have, that is 2 into, can I write 0.4 delta naught minus, because we have minus 0.4 delta naught, it is a stabilization. That is, I can write it as minus 0.8 delta naught, or 8 dq is the crystal field stabilization energy CFSC for this particular complex. If at all they are asking hexa aqua titanium 2 complex, what is the CFSC? Minus 8 dq or minus 0.8 delta naught. I will take the same one, vanadium, aqua complex only I will take it, 6 times 2 plus if you are having, that is vanadium 23, that is it is a 3D3 system, 2 electrons of the s orbital has been removed, 3D3 system. You have 3 electrons, can I fill 1, 2 and 3 electrons like this? Right? So this is a 3D3 system, 3 electrons. That means CFSC of this will be, that is minus or 3 into minus 0.4 delta naught. That means minus 1.2 delta naught, or 12 dq is the CFSC for this. As simple as that, CFSC calculation is done. If at all they are asking which is a stable complex, minus this one or this one, this is more stable than this. Why? Because this has a CFSC minus 1.2 delta naught and this has a CFSC minus 0.8 delta naught. Right? So let us now move on to the next complex, student. That is, for example, I am taking Cr, water only I will take it. Water 6 times 2 plus 2 complexes I will take it. I will try to take 2 complexes. One is Cr water 6 times 2 plus. One another thing is Cr ammonia 6 times, both are neutral ligand, 2 plus. Right? So you have to predict the crystal field stabilization energy for this complex, and straight away answer this question, student, and then I will explain why so. In this, the crystal field stabilization energy is chromium, it is 3D4 system, because 24 oxidation state, atomic number, 2 electrons of the s orbital has been removed, that is D4 system it's a D4 system. You have 4 d electrons you have, that means what will be done is, just try to understand, you have 2 options now, that is 4 d electrons you have, one you filled here, second one you filled here, third one you filled here, fourth one where to fill is the question. That is, fourth one, 2 options you have. One is, 4th electron can be kept here, or 4th electron can be paired here. Are you getting my point? Very, very important, student. This point is very, very important. That is, this will decide everything. That is, the fourth electron can be placed over here by pairing the two electrons, or you can put it on the Eg orbital. Rather than putting on the T2g orbital, you can put it on the Eg orbital. So that all depends on what decides that. That all depends on, students, what is called as our delta naught and pairing energy P. These two will speak about whether to put the electron on T2g orbital, or it has to be whether to put the electron on the Eg orbital, or it has to be paired on the T2g orbital itself. Continue what?